Welcome, everyone, to another episode of IT Visionaries. And today we have a special guest. He is the CTO of a company called Ansys, Prith Banerjee. Prith, welcome to the show.
Thank you, Albert. Great to be here.
All right out the gate, for all of our audience who may not know, please tell them what is Ansys, because this is a big company. It is publicly traded on the NASDAQ. For anyone who wants to look it up, ANSS is the ticker. Tell everyone, Prith, what does Ansys do?
So Ansys is a leader in engineering simulation software. So what that means is we help companies around the world in developing products that you sort of rely on every day. And the products can be electronic chips, mobile devices, to cars, to airplanes, and frankly, everything in between. So our customers use our simulation software to design and simulate their product in the digital domain, means completely on the computer, and without the need for expensive, time-consuming physical prototyping. Ansys today is a company of about 5,000 employees. We're headquartered in Pittsburgh, and we have about $2 billion in revenue.
For anyone who hasn't gotten a chance or can't conceptualize what I'm talking about, go to Ansys's website and check it out. Scroll down a couple pages and you'll see a picture of what appears to be like a jet engine turbine. And it's got data on the screen, and it's got engineers that have a iPad of some sort, and they're looking at it and they're trying to figure out, I guess, new ways to develop this turbine so it can be better. And like Prith said, without the need for physical prototyping, because the old way was you'd have to machine parts, implement it, and then test. Now with Ansys, you can simulate it, figure out what parts you need to machine, then of course develop the parts, add them, or buy vendor parts and test physical machines. Is that right?
That is correct. And let me give you another example, right? So in the past, when people say, suppose you're an airplane company, right? And you're trying to invent the new way of doing this airplane wing. So in the past, people used to build clay models of an airplane wing, put it in this gigantic thing called this wind tunnel, and push wind at 600 miles per hour on that clay model of the wing, and to see if this Bernoulli principle, right, provides the right lift for the wing or not, and at what wing shape and inclination will the plane fly, right? Or at what point, if you bend the wing a little bit, it will stall, right? So you had to build this huge clay model of this airplane wing, put it in this gigantic wind tunnel, tremendous cost, right? And you could only do 2 or 3 different wing shapes at a time, right? Because it is very expensive to build those wing shapes and to reserve time on the wind tunnel. Fast forward to today, with Ansys fluid simulation, right, called Fluent, we can simulate with the utmost accuracy exactly how those fluid flow will happen over the wing shape. And instead of one wing shape, you could do 1,000 wing shapes all on the computer. You don't need the wind tunnel. You don't need the clay models. So your cost gets reduced and your time to market gets significantly enhanced. That's the power of simulation-based product innovation.
Yeah. For those people who are just listening to what he's talking about, Prith's talking about literally months. The old way is like months. It takes months, maybe even years of constantly developing different shapes to model. Like Prith said, with now computer simulation software, you're able to, I don't know how many you can model a day, like thousands of variations a day, like rotate it 1 degree, rotate it half a degree, rotate it back half a degree, all types of different things. It's calculating an immense number of data points. Give us an idea of the engineering feat that goes into a software like this, because to your point, this isn't, like I always joke, I make fun of companies that make like image filters. You know what I mean? Like you mess up a filter, not a big deal, right? Prith, if you make a mistake, this is a big problem. Give us an idea of what kind of engineering goes into an application like this, because the amount of data points you have to capture, be able to measure, calculate. I can't even begin to think of how many different variations there are, but like you said, it's also got to be precise and accurate.
Absolutely. So the world around us is governed by laws of physics. And in the fluids world, the physics equations are called Navier-Stokes equations. These are things called second order partial differential equations, very, very complicated math. Now, you cannot actually solve those equations analytically. You have to use a computer to solve them. And the technique is called numerical methods. Now, numerical methods means you take a particular sort of a product like an airplane wing, and you essentially break it up into very, very small parts using sort of methods called finite element methods or whatever. And for this each small part, you say, here is the Navier-Stokes equation as applied to this one finite element. Then let's move the other element. Let's try to solve it. And essentially, you're solving hundreds, thousands, millions of these different points, and you build it all together very precisely, very accurate, extremely hard. And you said, Albert, that we build complicated software. Absolutely. And our software simultaneously has to solve these 4 different things. One is they have to act, you have to do it fast, right? If it takes you more than 24 hours to forecast tomorrow's weather, right, it doesn't do you any good. So you have to do it much faster. Now, to do much faster, you can do it with much less precision, much less accuracy, but that doesn't help you. So you have to do it fast and accurate. And once in a while, these things don't converge. So it needs to be robust. And the last thing is it has to be easy to use. If you have to have a double PhD to solve a fluids problem using Fluent, you have lost the problem, right? So you need to make it easy to use. These things are sort of contradictory things to each other, right? You can make it much faster if it is less accurate, but you need to be fast and accurate and robust and easy to use. And this is why the Ansys software is so treasured by people around the world, right? And we have physics software for fluids physics. We have software for structural physics, for electromagnetics physics, for photonics physics, for semiconductor physics. You name the physics in the world, there is a way to simulate it using Ansys software.
So this is super fascinating because you mentioned one moment ago this usability factor. And I remember when I saw some instrumentation for industrial manufacturing equipment and some of the software associated with it, by default, it was not usable to begin with because of the numerous fields and variables that have to be entered. Now, you're probably in the same boat, right? When someone's engineering a new machine, a new structure, a new whatever they're engineering, the reality is there's tons of little things that a person has to input, right? Tons of inputs that they're probably putting in and modeling. So you have to build, give us an idea of what goes into like the thought process of like what the interfaces have to look like, because they have to be able to accept a lot of data points. And also it has to reference, you have to have immense databases of referenceability. So for example, if I choose to change the element in, let's go back to that wing example. If I pick, I say I'm going to use this metal and I'm going to move to this metal, you need to know the difference in weight. You need to know the difference in, like tensile strength. You need to know the difference in temperature resistance, because obviously temperature fluctuates from depending on the use case application. I'm sure companies use your software to model out like drills for drilling deep rock, like the oil and gas industry, when they're engineering things that have to move through hard places, like you have to factor in the material that it's cutting through. Give us an idea of how you guys prepare for this type of input. Of course, you've built something today and you're going to add more to it, but give us an idea of like the infrastructure and the preparation and planning that has to go into this in order to even recognize what is involved in order to make it usable. Because you have to, of course, know all the fields that are going to go in before you can ever begin to make something even user-friendly.
Absolutely. So let me give you sort of 2 examples from 2 different industries. So let's look at the automotive industry, right? And in the automotive industry, all the big car OEMs are looking at sort of electrification, right? I mean, you look at,
sure,
our president has said, hey, we have to make everything has an electric car, right? So when you look at the automobile today, it's a thing that is driven by a human car, right? And it's driven by an internal combustion engine. This sort of gasoline engine has been perfected over the last sort of 50 to 100 years. When that is being electrified, means that engine is replaced by electric motor, right? Now, how does electric motor run? That runs on batteries. So you have to, and now suppose you are trying to do a fast electric car. So for example, we are partnered with Porsche Motorsports, right? Porsche is fast, sports car company that fastest cars in the gasoline area. They're trying to build a fast electric sports car, right? So you would think that the problem is, so I'll change the the gasoline engine with electric motor. And because I want it fast, I will do a super duper really large electric motor. Now, when you do a really large electric motor, which you can model with Ansys Maxwell, right? So you can do that, but then that requires a large battery to drive the motor, right? Mm-hmm. Now, the batteries can be modeled through our Ansys Fluent. So okay, you got a gigantic motor and a gigantic battery. Well, now the weight of the car goes up, right? So you try to build a really fast electric car, you got this ginormous electric motor and ginormous battery, right? The inertia goes up, and so, that doesn't work, right? So I have to do a system level design. If you are trying to build this most complicated, beautiful electric car, right? That has the external aerodynamics, the fluid flow will just go right. You have to use Ansys Fluent to model that thing. You have to use Ansys Maxwell to use the electromagnetics for the motor and the battery system with the Fluent and so on. So we have partnered with Porsche Motorsports to build such electric car. Another example, Lucid Motors, right? They are like the Tesla, right? Essentially, they're trying to build a really super luxury electric car. Both these companies, Porsche Motorsports and Lucid Motors, have used Ansys technology to build their next generation electrified cars. Fast forward to change to the sort of a aerospace industry, right? I mean, all these planes, airplanes, et cetera, right? They are trying to be electric and automated, right? So let me focus on the autonomous part, right? So we worked with Airbus Corporation in building an unmanned aircraft vehicle, right? So in the world of autonomy, the human designer is gone, right? So essentially, we human have the five senses. We see things, we hear things, we touch things, and so on. So we have at Ansys created physics-based sensor technology using radar sensors, camera sensors, LiDAR sensors. You can sense the world around us. Those sensor data goes into the thing, and then the actual computer will do the sort of autonomous decisions and so on. But when you're building this autonomous electric car or a airplane, right? You have to do all kinds of different scenarios. You're driving this car on San Francisco Golden Gate Bridge at 9 a.m. in the morning when it's sunny. You would like to say, what happens if it's 9 p.m. and it is snowing in San Francisco? You could actually create these scenarios using simulation. So we have partnered with Airbus. We have partnered with, there's a company called, organization called Air Race E, which is trying to build this autonomous aircraft, right? Usually autonomous, which is sort of co-funded by Ansys and by Airbus, right? So there are all these teams that are using Ansys tools to build an autonomous aircraft for the future. So those are some amazing things that we are helping our customers to solve.
How about how do you solve for this? Because I would assume the pace of engineering and innovation keeps increasing, right? There's more discoveries are being made every single day. Even though we have the laws of physics, the reality is people are trying to defy physics. They're introducing new materials, new designs that can capture more data. There's more sensors now at the edge of every device capturing more data, which probably feeds into your data pool of what will happen if you introduce this new material, if you encounter these new elements, right? You're constantly intaking more data so that you know exactly what will potentially happen because you've now sensed it from another data source potentially. Talk about how do you prepare your systems to intake all this information? Because the amount of information that is currently being discovered right now continues to increase, right? The laws of physics, like we said, the laws of physics are the laws of physics, yet humans have been trying to defy physics since the very beginning of time. And so we're discovering things all the time. How do you guys keep the data constantly up to date with the most recent discoveries?
Absolutely. And this gets to the core of my job as CTO. As CTO at Ansys, I'm responsible for setting our long-term technology strategy. And the core of your question is some of the work that we're doing on the use of AI, machine learning applied to simulation. And as you're getting all this data from either measurements from sensors of assets or the measurements of sort of data from simulation, right? You're creating these ginormous set of tremendous amounts of data, and there's sort of patterns in the data that you can learn from. So what we are doing at Ansys is to use AI machine learning to learn from this measured data and from simulation data to accelerate the way you can actually do these simulations, right? So rather than relying on the traditional numerical methods using finite element methods, finite volume methods, what we are doing at Ansys are to accelerate these things by factors of 100 or 1,000, where this fluid flow simulation through AI/ML will be deeply accelerated. Now, what good is it? Well, in a given amount of times, in the past, a user would have submitted a job, right, overnight. I mean, at 5 p.m., at the end of the day, they submit a job, and they would like to get the result back at 8 a.m. in the morning, right? So you have that sort of 10, 15 hours of compute time. And within that, we kind of used to take the number of mesh points and so on, right, to make sure the job returns in about, say, 8 or 9 hours. Today with AI/ML, we can accelerate it so much that instead of doing one design, the designer can have access to 100 different designs. So the next morning they come in, they can do some really amazing product innovation for the most optimal parts. Now, you asked another question, Albert, about these new materials that are coming in, right? So all these solvers that we have, suppose we have a part which is a mechanical part, right? And in Ansys mechanical, in structural simulation, you are supposed to say, here is my input condition, here's my boundary condition, how much will it bend, right? How much will it bend is determined by the Young's modulus of steel, which is a material properties, 0.2212, right? So in the past, we used to program in the Young's modulus of steel, that's number, into the solver. A couple of years ago, Ansys acquired a company called Granta, which is a materials intelligence platform. Now we have access to 100,000 different materials properties. You give me wood, you give me aluminum, plastic, steel, that data is entered and it is continuously updated. Now, if you have an alloy, right, you are trying to build a bike, not with steel, not with aluminum, but with 70% steel, 30% aluminum. Or I can tell you the right alloy to use is 22% aluminum and 78% steel. You could do all this analysis, right, purely on the computer, create this alloy specification, and then send it for manufacturing using 3D printing, right? You don't have to do it with injection molding. This is where the industry is headed.
Yeah, that's unbelievable. I used to work on a project for Carpenter, which is a metal fabrication company. They would make aerospace metals as well as surgical metals. And this predates a lot of this AI/ML that you're talking about, like, right? Like the way that they would come up with their alloy blends was through the old guess and check method, like we had that we were taught in school. Hey, if my hypothesis is, if I mix this element with this element, this alloy would be lighter and stronger. Now you're saying you can just model it because you have all the data properties of all these different known compounds, elements, minerals, whatever the idea. You have these things all indexed. And so people are running more like computer models to figure out what's the best first experiment. Give us an idea from different industries of how much time has been reduced, I guess, in the R&D phase, because R&D for a lot of these companies, whether it's automotive, whether it's aviation, but like whatever it is, when you're making new things that didn't exist, a significant portion of your time is spent in research and development. You're trying to build something that doesn't exist. We know it takes years, right? It takes years and stuff. Give us an idea. Have customers, have people told you like how much time is being cut off of the dev cycle because they can now model this?
Yes, absolutely.
Model more variations. So
again, this is a constantly changing metric that every year we are trying to make it run faster, bigger, better, etc. Right? So, but there are actually data from the Aberdeen group that shows the power of simulation. So the one data point that I will just share with your viewers is the following, right? So you look at the total cost of a product over an entire life cycle, right? And when you are designing the product, you have this ideation phase, concept phase, design and testing phase. But that's when the product is done, right? Mm-hmm. The cost of the product, be it an aircraft engine or an automotive or a semiconductor chip or whatever, right? 90% of the cost of that entire life cycle is determined at the time the product is built. because that product, I mean, the aircraft engine, right? It will be in the air for 20 years, right? And then you have to repair the engine, do this, etc. So there's a lot of cost to this aircraft engine that you build. So 90% of the cost is determined at the time of the production. That cost, if you could reduce, and actually we have done it through life cycle simulation cost, right? We can simulate this product, right? This engine that you built as designed, as manufactured, this through these 52 airplane blades you're actually manufacturing through 3D printing or whatever. Then this aircraft engine is sitting on an United Airlines plane, right? It's flying from New York to San Francisco for 20 years and having all kinds of bird strikes, right? We can model all of those, right? And so, well, if you have a bird strike, this blade will break and you will have to, so instead of this making the blade with steel, we should make it with this alloy. So the bird, when it strikes, will not have. So we could do all of those things through simulation. And this is the kind of advancement that we have made in the industry. So we have reduced the time to design products by sort of more than 50%. Literally every year we try to do this. We have reduced the cost by more than 30%. So these are the kinds of benefits of simulation-based product innovation.
This is fascinating because I'm thinking about one of the things that we had a hypothesis of back when I was in grad school was this idea of like the journal of null results, that there's so many results that people didn't get an answer from, like where they didn't get a successful outcome from, that they never get published or never get shared with anybody. So a lot of people kind of remake the same mistakes. Well, simulation software reduces making those mistakes because you can simulate it right away. You'll get a null result. Then I was thinking about, as you were talking, how many companies have attempted to, let's say, make something, but let's say for whatever reason, over the course of a year, they weren't successful, right? And there's tons of products probably out there, tons, but probably thousands of products that people thought that they were going to make over the course of time that never actually got anywhere because they never got the questions answered. So arguably tools like this are now they're going to address whatever barriers there were to releasing products, like, because you'll be able to find the answer faster. One of the things that we were checking out inside of Ansys's website was this commitment to academia. We saw this really cool program of students, academics, Ansys academic. You have an academic background, or looks like it's now being brought to the university level, possibly even lower, where I guess kids or students, are they learning how to engineer
Absolutely.
using these tools?
So this is a great question. So as you mentioned, Albert, I spent 20 years in academia as a professor at the University of Illinois, Urbana-Champaign, and Northwestern. So academia is in my blood. So when I joined Ansys as CTO, made sure that we had a very strong academic program. So today, we have this academic program with more than 2,500 universities around the world, right? And these students are normally these. If you're an engineer in a large company, commercial company, the tool would cost $50,000, $100,000. It's a very expensive piece of software. But for academics, for these students, it is free, right? We want to make sure that all these brilliant engineers who are going to sort of their undergraduate, first year, second year, third year, etc., right, in learning introduction to mechanical engineering, they can download the Ansys software for free. A statistic that I have is there have been more than 1 million downloads of our Ansys academic software, right, across these sort of 2,500 universities. Many universities are using Ansys as part of their curriculum. Like, for example, this year we had this program with the University of Michigan where we are redoing 5 of their courses to use Ansys in their introduction to mechanical engineering, introduction to aerospace, and so on. We are doing it at Cornell. We are doing it at the University of Illinois, Urbana-Champaign, my alma mater, and so on. So this is how engineering education is getting transformed, because in the past, these kids used to go to a lab and they say, using that, the example of this clay model and the wind tunnel, right? Today, on a computer, they can literally see these things. And there are all kinds of what-if scenarios that you can do with simulation that you couldn't do really. For example, you're trying to explain, here is a pump, and inside the pump, there's a thing called cavitation. A cavitation is a bad thing that happens, there's bubbles and so on that happen, right? You cannot actually sense if there is a cavitation happening in the pulp in the real thing, right? Because you cannot see it. If you probe a thing, that it will stop acting as a pump. But through simulation, you can create these things. I mean, the concept of digital twins, right? You can actually create these what-if scenarios, create virtual sensors. So the students at the universities can say, oh my God, what if I did this? What if the temperatures increase and so on? And this is the way we are transforming academic education in the engineering world.
Yeah. Give us an idea. The digital twin, you just mentioned it. A digital twin is a virtual representation serving as I'm reading a definition. A digital twin is a virtual representation that serves as a real-time digital counterpart of a physical object or process. So this is the exact thing you're talking about, which is simulating whatever it is that they're trying to build in real life. So in that example that Prith was just using, he was talking about bubbling and contained within a vacuum. So maybe perhaps like some type of, like you said, like a pump of some sort. If there's some type of problem causing bubbling, it would cause other problems, leakages. As he just said, you can't probe it. You can't stick anything into the vacuum because then it would lose all of its vacuum properties. So the only way to do it is to create a digital twin, a digital virtual representation of the pump, and test variables that way. Because otherwise, the only other option is to build, and back to where we were talking about before, guess and check. So for those of you guys that weren't familiar with, and Prith, please correct me if I misspoke. I wanted to make sure our audience knows what a digital twin is because you just mentioned it. Absolutely.
So you're right. I mean, again, we are. So a digital twin, as you said, is a connected virtual replica of a physical entity, and this whole area has become very, very exciting and hot. When I was CTO at Ansys, at Schneider Electric and ABB, I used to live in the world of digital twins, right? So you have any asset, right? A breaker, a transformer, a robot, or whatever, right? People are putting now IoT sensors on that asset, collecting data, and based on the data, you're trying to look at the past behavior and predict future behavior, right? So you are trying to predict when this aircraft engine may go bad, right? So you can replace the engine before bad things happen, right? This is the whole power of engineering, right? So doing better predictive analytics. You can do much. So people can do these digital twins based on collecting data alone, but data-based predictive analytics we have found is sort of accurate to maybe about 80% accurate. Through Ansys simulation-based digital twinning, we are able to increase the accuracy to about 90%. But the latest innovation that we have done is called hybrid digital twin, where we combine data analytics with physics-based simulation and get the accuracy to about 99%. And once you have that accurate prediction, you can predict the future. You can avoid all kinds of bad things, be it in oil and gas areas or automotive or aerospace or high-tech manufacturing. So super, super exciting area.
Yep. So, I mean, obviously the use case applications here are in just about every industry. What industries or what advancements are you most excited to see? Me personally, listening to you talk, I'm excited about the health and health equipment industry, seeing what kind of advancements can be made there. How about you? Do you have any personal hopes, wishes? Because you probably see some really cool use cases, test cases of the application.
So we are today working on some sort of use cases in three broad areas for digital twins. One is in what we call industrial flow networks, right? So you look at these large oil wells and so on, right? The oil and gas companies, they're upstream, downstream, and so on, and they have these flow networks having tens of thousands of valves and pumps and compressors, and we can take a digital twin of individual pumps and compressors as well as flow networks and do it very, very accurately. A second use case is in general in sort of electrification. I kind of mentioned this Porsche Motorsports case, but when you're building this whole electric cars and so on, right, to come up with a digital twin of this electric motor drive, battery system, and so on, we have done a lot of work with various automotive companies in this area. Third use case is sort of heating, air conditioning, large buildings, right? Is large building, you have air conditioning and so on, chillers and coolers and so on, and we can do through digital twinning really, really exciting predictions of the future. So that's where we are today. You talked about the future. I am personally, like you, Albert, excited about healthcare as a really big area for simulation and for digital twinning. Just look at the human body. We have these amazing organs that we have, right? The human heart. The heart is such an incredible device, right? That beats 72 times a minute. That is because there's electrical signals going to the heart that comes 72 times a minute. In response to those electric signals, the muscles in the heart, they contract. And when they contract, the atrium, which is this one of the heart chambers, right? It pumps blood from the top part of the valve to the bottom part. And at the exact same time, the mitral valves open up. And then in the second step, The ventricle pumps blood and it goes through the cardiovascular system because another valve opens up. Again, the human body has this amazing parts, right? Now, in the past, and suppose you had arrhythmia, right? You have this, your heart is not beating right, and you have to invent this new pacemaker that will fix the arrhythmia. So people had to build the pacemaker and test it on 5,000 patients to see, does it fix my arrhythmia or not? In the future, and actually today, we are working on sort of heart simulation, right? With a very, very accurate heart simulation where we are modeling the electrophysiology, the muscle movement through structural, the fluid flow through the fluids models and so on, and doing it really, really accurately. And we can take a patient-specific workflow where Prith has a heart problem, goes to the hospital, right? Does an MRI machine, takes that MRI scan, that is automatically converted into sort of STL files, doing the meshing, do the simulation, and you can literally say, if I put this pacemaker right here, will it fix the problem or not? Now, isn't that amazing? Yeah. We are talking about digital twins of a human heart, digital twins of Prith, digital twins of Albert, personal digital avatars. This is where the world is headed.
Yeah, it's pretty insane. And for anyone who sits down and thinks about it, like think about all, today there's pacemakers, as Prith just said. There's also synthetic, people are trying to create replica organs. It hasn't been done quite yet, but fake lungs, fake hearts, something, if people that need transplants but currently can't get one, like in the future, will there be robotics? Like, could your heart potentially be replaced with a robotic heart instead of a transplant heart? Different organs. There's so many things that people are probably, like you said, just asking the questions. We don't have answers today, but like you said, you need to ask the right questions. Ansys, the tool, is going to model it up for you, and it's going to put you down a path of engineering faster. What are when you think back to your career? I mean, to me, this is when we used to watch I can date myself. It's fine. I'm 42 years old, but when we used to watch movies of the future, right? It was always just like Iron Man. There was always like an AI that was able to always figure stuff out for you. That could say, hey, if you do this and this and this, almost like helping you solve a puzzle, right? But like with Ansys, it's like you're kind of getting there. Like we're kind of getting close. Ansys is the Jarvis for Iron Man. He is for Tony Stark, right? It's like helping us figure out things. Is this something you envisioned as a kid, or did you give us an idea? Like, did you think this was possible? Like, I'd love to understand this, because you mentioned before you were in academia and you've, built companies and started companies. You've done a lot of great things, but this is just a whole different ballpark compared to what you were doing before. I'm curious, like, did you think this was possible?
Absolutely. So as I mentioned, right, so I was fortunate to have spent sort of first 20 years in academia at the University of Illinois and at Northwestern. Then I did sort of 2 very small software startups based on the work that I did at these universities. The last 15 years, I've been working in various companies. I was head of HP Labs, CTO at ABB, Schneider, and now at Ansys. Yeah. I had never imagined that when I was in academia, I was doing work on sort of parallel algorithms for electronic design automation. I wrote a book on that topic. But at the time I was doing the research, the year was 1985, 86, 87, right? I'm dating myself. The industry was not ready for parallel algorithms. Come on, we can solve all these problems on our workstation. But that's what academia do, right? Professors imagine the things 20 years from now and what will be needed. Fast forward today, right? In 2021, Ansys, right? Our core solvers, Ansys Mechanical, runs on HPC. We have these things running on 4,000 cores. Ansys Fluent running on 200,000 cores, right? So when you have this large sort of a really complicated problem in oil and gas and so on, right? And researchers at KAUST University of Technology working with Saudi Aramco, right? They are solving this problem running on a Cray with 200,000 cores using HPC. These are the kinds of things that when I was in academia, I was working with my PhD students on solving these problems. And fast forward, it's there today. So how cool is that?
Yeah. I mean, I will say this, this interview has been a lot of fun. you're fired up, and I love it. Like when I hear you talk about use cases and how you see the future coming and some of the things that customers are doing with the product, you are fired up. We've had some people not as fired up as you, but like you. So that's why it's fun talking to people that are just super passionate about what they're working on. That's no question about it. Prith, it was awesome having you on the show. But before you go, it is time for the lightning round. The lightning round is sponsored by Salesforce Platform. Let me restate. The lightning round is sponsored by Salesforce Platform, the #1 cloud platform for digital transformation of every experience. Prith, this is where we ask you questions outside of the world of work so that our audience can get to know you a little bit better. You ready?
Absolutely.
All right. So, are you a gadget and gizmos guy? You seem like you would be.
I am. I'm even from when I was young, as a young kid, I built a electronic flow meter when I was in school. So people didn't have sensors and actuators or whatever, but I built that for a sort of science talent scholarship in India. So yes, I am a gizmos guy. I love gadgets.
So what's a current gadget or gizmo that you just like a lot, or you would recommend other people checking out?
So I am actually playing with some of these audio and video gadgets, right? I mean, I just installed a Dolby Atmos sort of system in my home, right? And the sound experience is just an amazing experience, right? And I'm driving my wife nuts with all the music that I'm listening to, but it is. I mean, the experience that you have is absolutely outstanding.
Yeah, I only have one little clip speaker, although I love music. What kind of music do you like?
So I am actually trained in Indian classical music. I play an instrument called the sitar that was made popular by Ravi Shankar. So I play the sitar at home, and I've been playing it for the last 30 years, and I'm reasonably good at it. So I enjoy playing that music, but I enjoy listening to classical music, both Indian and Western classical music.
Do you like listening to music while you work?
Absolutely, all the time. Like, this is why I have my good microphones with me.
I've read research that says classical music can help open up the mind. Do you believe that's true?
I absolutely believe that is true. In fact, I am no Einstein, but it is known that Albert Einstein also was a big sort of a supporter, fond of classical music. And let me give you actually an example of how music is related to just innovation, the world of innovation. You are mentioning during the interview that when people are inventing new things, there are once in a while it will be working, and but 1,000 times it will fail, right? So
that's right.
You have to explore all kinds of different things, and then once in a while it works, right? In the world of music, right, there are these structured musical things, right? Well, you have Beethoven's Ninth Symphony, right? And you have to play that music exactly the way it has been written up by Beethoven. But in Indian classical music, right, you are given some broad constraints. Here is this raga bhairavi, right? And he has to these notes. But within that, you can improvise just like a jazz musician. So being trained in the Indian classical music, right, the way I have been, right, I can play the sitar, and every time I play Rag Bhairavi, every time I play it a little differently, because it's my innovative sort of nerves or whatever in the brains that they're acting up in a different way, right? And I think there's something about the relationship to the jazz music, the Indian classical music, and so on, about, yes, there's a structure, but then you can do all kinds of creativity around that structure, right? Same thing in the world of innovation, right? If you only do innovation one way, you're just putting bricks one after the other, you will build a really boring product. But if you allow yourself the jazz musician creativity, you can actually do interesting things. So in my world, I have been able to combine the world of music, Indian classical music, with the world of the CTO. So I enjoy it.
There you go. And I love that. And it further supports, we've cited countless studies here on IT Visionaries over time, and I'm a firm believer of it, that most of the world's innovations actually come from outside outsiders. Outsiders typically have the solution. And part of it is probably because, like you just said, if you've been going at a problem one way the whole time, then you will continue to solve a problem that way. Sometimes the solution is not that way. It's something different. So I think it's fascinating that you're almost like experimenting with your own mind, constantly trying to open it up to new avenues.
Absolutely.
Prith, it was awesome having you on the show. Thanks for sharing a lot about what Ansys is up to. For those of you listening and have never heard of Ansys, go ahead and check it out. That is the proper spelling of the company is ANSYS. It'll be linked up in the show notes below. Super fascinating company. The more I read about it, the more. And then now that you've heard from Prith exactly, I can't stop but start to wonder what kind of innovations this is actually going to unlock. Like people always talk about what's the future going to look like? I mean, I don't even know now that you can build things. And what used to take you years to figure out, it can take you days now.
Absolutely.
Which is crazy.
What we do is, I will leave you with a final thought. The world around us, as I said, is governed by the laws of physics, but it starts with atoms and molecules. We can simulate atoms and molecules to parts, to chips, to airplanes, cars, rocket ships, and entire systems. So we say we can simulate from atoms to rocket ships. This is where we are headed today.
Super fascinating. I would imagine this product will be inside of any company that makes physical products probably in the future. Who knows?
Absolutely. Hey, it was great speaking to you. Thank you so much. Thanks for asking me to join the podcast. Really enjoyed it.
Yes. Thanks for joining us today on IT Visionaries.